So now that we know some of these, we had an overview, we're going to take you a little bit more carefully through some of these aspects. And I'm going to begin to prepare you to use some of these features and begin to actually get performance out of this kind of code, okay? And someone asked a very good question yesterday, and I gave a okay answer yesterday. I think it was the answer about API and the GPU API. Who asked that question yesterday? Is he still here? Were you the one who asked the GPU API question?
What question are you talking about?
Rather than handling threads directly, would it be better to just use API, right? And what I answered yesterday was the APIs, in the previous GPU generation are not the answer. However, after the end of this class, you will probably start to recognize that CUDA can really make use of some domain-specific APIs, okay, such as, if you're doing molecular dynamics, they're probably going to need to be a molecular dynamics API that suits the application domain, but also hides some of these thread complexities from, typical programmers. So, that's one thing that we're going to also come back to, hopefully towards the end of the semester. So, what we talk about so far is the kind of a programming abstract view of what CUDA is. But this is the beginning of the point where we're going to open up the hood a little bit and let you start to see some of the underlying engines, transmissions, and all that stuff, just so that you can actually understand how to drive this thing very fast. And so we're just beginning to get into some of the hardware realities here. And the GPU, one of the reasons why we're using the GPU, for this class, is that, over the years, over the past 4 years or so, the performance improvement of the general purpose CPU has slowed compared to historical, trend. And the reason why it slowed down is because of the power consumption issues. These chips are just running too hot. And the reason why these chips are running too hot is because CPUs have been designed with the philosophy of very high clock frequency. And whenever you run the clock frequency at very high level, you need to be able to drive the current very quickly, so that consumes power. And also, the actions happen very quickly, so you do the switching also more quickly. And these things multiplied together, gives you a huge amount of pressure in the power management. As a result, the CPU vendors have not been able to raise the clock frequency as fast as the historical record shows. On the other hand, things like GPU have been still improving in terms of their computational speed because they are based on a totally different philosophy. What these GPUs do is they don't really raise the clock frequency nearly as aggressive as the CPU people, but they just keep adding execution units into the chip. So if you compare the clock frequency, the internal clock frequency of G80 is actually 1.3 gigahertz. And the Intel Core 2 dual chip is 3.0 gigahertz. So there is about 2.5 times faster clock in the Intel chip, but there are a whole lot more execution units in the GPU. So at this point, the performance ratio between the GPU and the CPU is right around 1:7. Okay, and so that's the raw computation power. If you compare the peak maximum performance of a state-of-the-art CPU and state-of-the-art GPU, it's about 1:7. But that's not the whole story. the GPU used to be not very programmable. And what I just taught you in the last lecture is that now it has become programmable. And it supports 32-bit floating point precision. And so for those of you who are thinking about scientific computing, a lot of scientific computing still require double precision. And that actually would come in about 3 months from NVIDIA. So they're going to have a double precision hardware coming up soon. And it offers lots and lots of gigaflops. And the GPU, but one thing that is very, very interesting is that there is pretty much a GPU in every workstation and PC these days because of the graphics display and games and so on. So in many ways, the GPUs are becoming as popular as CPUs. And people have very pervasive access to this kind of hardware. And historically, for parallel programming, we always had this problem where when someone did a heroic effort getting performance out of a piece of hardware for application, only 10 people can use it. Okay, and that doesn't get you very famous. Okay, but here, the G80, the G8 series has sold more than 5 million copies to this day. And whenever you do a heroic effort, if there are millions and millions of people who can use it, now you can become famous. So that makes a huge difference in terms of parallel processing mentality and application porting. So there are two very important differences in the CPU and GPU design philosophy that you need to keep in mind as you look at some of the lectures that we're going to be covering in the next several lectures. The GPU is really specialized for compute-intensive, highly data parallel computation. Okay, so if you don't have a lot of data, if you don't have a lot of parallelism in the compute of these data, GPU is not going to do you any good. And turns out that it's actually very common when these applications require long execution time, they do have a lot of data. Okay, so it's very common the case that you will have some a situation where you have data parallelism. So when people design a typical CPU, the CPU would look like a piece of control logic with some ALUs, typically about 12 to 16 function units for a CPU. And then there will be a fairly large cache. And this cache memory can be organized into the hierarchical arrangements. The first level cache is typically about 16K bytes, and second level is about 256K. And the third level right now is between 1 meg and 9 meg, okay, for these machines, just so that you get some concrete feeling about these things. If you look at Itanium 2, the cache is actually much, much bigger than the CPU, than the function units and control. You really don't see the function units, you see the cache on that chip. Why is that? The reason for that is because the CPU design philosophy is to get as much data as possible to sit on the chip so that the CPU can actually access the data in very short latency. Essentially, single cycle for first level caching, about 5 cycles for the second level caching, and about 12 cycles for the third level cache, compared to hundreds of cycles if you needed to go to DRAM. And the CPU pipeline is typically designed to tolerate cache hit latency. 1 cycles, 5 cycles, maybe 12 cycles. So that's called out-of-order execution. Okay, and the CPU will rearrange these instructions in order for some of these memory accesses will take 5 cycles or 12 cycles to complete, while it would look at some future instructions and see if they can do some busy work waiting for that 5 cycle or 12 cycle latency. All this design costs transistors. Okay, so that's why on a comparable chip you will see a small number of CPU cores, because each CPU core requires all this logic. Okay, whereas the GPU design is based on a somewhat different philosophy. It says, I'm going to design the equivalent of a CPU core in a very small, with a very small amount of memory. So I'm not going to try to put a lot of cache memory on the chip. Okay, I'm going to just put a small amount. And so I know that whenever I execute, I'm going to have, essentially a little bit control, a little bit of cache, and then a huge number of units. Okay, this was the SIMD thing that I was talking about, right? So you have a huge number of these execution units, and now you have a little bit of a problem. The problem is because not a whole lot of data is sitting on the on-chip cache, you will have situations where you have to go out to the DRAM to get that data, right? So right from the beginning, you design for DRAM latency. And the way to tolerate DRAM latency is not to execute instructions out of order, but rather have a huge number of threads that can execute on these function units. If one of the threads is trying to access DRAM, you look at these other threads and see if they're ready for using for execution on the function units. If you look at the matrix multiplication example, what happens is we will have 256 of those threads. Out of random distribution, you will see, some of the threads, accessing memory, and some of them will come back with data, and the others will still be queued up in the memory access interface, right? So as soon as you have some of them come back, you execute them in the function units, right? And that's how you tolerate memory latency. And that's why you need to have thousands and thousands of threads in this, in this chip to keep it busy. So, it turns out that the fast-growing video industry, essentially demands this kind of execution power in order to get you that, that sense of satisfaction. I'm sure nobody in this room ever experienced because you don't play games. On the other hand, a lot of people, require this kind of computation power in order to get more and more sense of reality out of these games. And as a result, the GPU computation resource is growing by about 2 times every year, okay? And that gives us a huge amount of growth. But on the other hand, it also gives a lot of, interesting challenges in, programming this kind of chip. You need to figure out how to generate all those threads. And someone asked, you asked us yesterday, in the CPU world, people typically, handle a small number of threads, probably dozens of threads in the current generation chips. And that has already been a challenge. So, how do you do this? That's why, if you look at the design of the CUDA language, it really does 2 things. Okay, one is it makes it very, very easy to generate these threads. You do a kernel call, and that's it. Give the configuration variable, and you generate all these threads. And the second one is the hardware can kick off those threads in one or just a couple clock cycles, so that when you generate threads, you don't end up spending all your time just generating the threads. They can do the work. However, the real intellectual difficulty in this thing is how do you actually organize your algorithms? How do you actually organize your data structures in order to enable the generation of these threads and also to run them efficiently? Now, I talked about split personality yesterday. So the dictionary definition of split personality is 2 distinct personalities in the same entity, each of which prevails at a particular time, and hopefully not both. So what does this have to do with GPUs? So what happens is that, when they produce the G80 CPU, they actually produce a piece of hardware with 128 of these, execution units called streaming processors. And we're going to actually go into a little bit more detail so that you can really understand the performance characteristics of these things. 128 of those essentially are used as a pool of execution units that can handle rastering and rendering and all that stuff. Okay, so when the graphics, the graphics execution commands come in, Then you will have the vertex thread issue, you have the geometry thread issue, you have pixel thread issue. All the graphics commands will be processed by these hardware interfaces. Okay, these are the things that deal with OpenGL and then DirectX kind of API stuff. Okay, that's the traditional graphics interface. The difference between this thing and the previous generation is that all these different processings actually all come in and compete for all this resource, right? But in the previous generation, you would typically have a pool of resources for vertex processing, a pool of resources dedicated for geometry processing, and they form a big pipeline. The reason why they went into this way is so that they can load balance better, because of some of the applications require more vertex processing, some applications require more pixel processing. By pulling them together, you can make use resources utilization better. Okay. However, once you have produced this set, you start to look more and more like general purpose processors. So you may as well create another set of hardware interface which does not deal with vertex processing, and it doesn't generate threads on behalf of these commands. Right? This goes back to the who generates the threads. So the programmers actually not generate threads through the kernel invocation, but then the threads will actually just be issued by this simple piece of hardware into all the execution units. So this is a separate hardware interface that gets turned on when you switch mode. And that is the execution base of the CUDA programs. So if you look at sort of the hardware products that are based on this, there are two examples. One is GeForce 8800 GTX, and one is GTS. So there are two different grades of graphics cards, okay, that you can buy. One is about $550, the other one is cheaper, I guess. So the maximum number of threads per block for both products is 512. Okay, this gives you a little bit of hint about how these things are going to be scaled. So you know what? You're unlikely going to see more threads per block in the future products. Okay, that number 512 is likely going to be pretty much fixed through the product generations. Okay, so you really need to think about not just getting more threads in a block, but also more blocks. The maximum size of each dimension of a grid is 65,000 blocks, okay, in each dimension. And you can clearly see the intention here. They want to allow people to generate lots and lots of blocks, right? Not lots and lots of threads in the block. The 512 is the maximum that they will support. So the product scaling is going to be the current generation. I'm going to support, let's say, I'm going to be able to simultaneously execute, let's say, 10, 15 blocks out of the huge number that you specify. So it will take a while for the chip to go through them, right? And the next generation, they will add more function units, then they can simultaneously execute more blocks. So you specify a huge number of blocks, and they will generate products that will each generation be able to handle more and more of the blocks at the same time, and that's how they scale. This has implications into how synchronization is done, how these things are designed. So you really need to keep this in mind. So the number of streaming multiprocessors, SN, going back to the terminology, we're going to actually go back and review all these things. Each one of these, 8, is a streaming multiprocessor. Okay, so there are 16 of those in the GTX. Now, there are only 12 of those in GTS. They execute exactly the same code. Okay, you don't need to generate code differently for GTX and GTS, precisely because of the reason I just talked about. You will be generating lots and lots of blocks. GTX will be able to handle more of those, will be eating up those blocks faster than GTS, but they eat the same total number of blocks, right? So device memory, GTX is a little bigger, and then GTS is a little smaller. shear memory per multiprocessors is 16 bytes divided into 16 banks. And this is likely going to be fixed or changed very, very slowly through the product generation. So remember, we have 16 of those multiprocessors, right? So each one will have 16 bytes of shear memories that all the 8 little guys can access the shear memory in parallel, okay? But that's it. Only those 8 streaming processors can access the shear memory. And the shear memory is actually divided into 16 banks. So this has an implication of what we call a bank conflict. For those of you who have taken computer architecture courses, most of the memory systems are banked anyway, and we always have to deal with memory bank conflicts. And that is going to be one of the lectures later on. Okay, so don't worry if it's not familiar to you. You can have up to 64K constant memory. The size is actually determined by the graphics API. Historically, graphics API limit the constant size to about 64K byte, and therefore, when they build the hardware and so on, they just use 64K byte. This is something that could be increased in the future. And there's a concept called warps. And you don't really need to understand warps, strictly speaking, because it's not a CUDA concept. Okay, from the programming level, you don't see warps. However, if you need to understand the performance of GTX hardware, you will need to understand warps. Warps is a subdivision of the threads in a block. Let's say you have up to 512 threads in a block. Every 32 of them start from thread 0. Every 32 of them form a warp sequentially. Okay, so you just chop up the 512 threads into 32 thread warps. Why is this important? It's important because in this particular generation of implementation, those 32 threads are going to be executed in SIMD mode. They don't have to in future generations, by the way. There may not be warps in the future generation. But for the foreseeable future, in the next few years, if you really want to get high performance out of these things, you need to understand warps for the next 5 years or so. Okay. So what is GPU good at? We talk about this data parallelism. And one thing that you also need to understand is the GPUs are highly, highly tuned for floating point arithmetic. So let's go into the memory model. This is a picture that I was alluding to in terms of the previous GPU memory model. What happened in the previous generation is when you execute a piece of code in the GPU API interface, you can marshal data in the sense that you can actually go to different memory locations and collect them into the input. Remember that input thing, input register, output register? Essentially, you collect all of them into the input registers, and then you can do the computation. But after you're done, when you try to write back to memory, the write interface is a pixel interface. What that means is when you write a pixel on the screen, there's only one data point. Okay? So each program can only write into one location. And if you need to write into multiple locations, it doesn't work. So you need to have something else that converts your output into some kind of form later on as a post-processing. So that's why it gets really hard in the previous generation. Another difficulty is that in most of the previous GPUs, whenever you need to read from multiple data locations, even if two pipelines need to read data from the same location, there's no mechanism for them to save memory bandwidth. There's no way for them to piggyback on each other. So both of them need to go out and do the memory access. That's the reason why in the interface, most of the GPU interfaces, there's a little piece of hardware that kind of looks at the traffic going by. And whenever it catches a case where two accesses from different ALUs going into the same memory location that happen in a very small time window between the two of them, the hardware will try to combine them together to save some memory bandwidth. And that's called memory coalescing. Okay? Almost all the GPUs have that kind of capability. It's highly guarded secret. They don't tell you exactly how they do it. It's their bread and butter. Okay? So, but everyone knows in the field that there's a piece of hardware, and you can even think about some ways to design it, but they can design it better than you because they have been thinking about this for a long, long time. Now, CUDA is a little bit different. In the CUDA interface, remember when you specify these kernels, you just essentially do the address calculation. Remember, you can just do the address calculation with your thread ID, right? And then you go into the global memory. So there's no constraint about where you can write, where you can read, right? So that's why in CUDA you can easily read from multiple memory locations into the same computation. You can write to multiple locations, and that makes programming a lot more flexible. Okay, and also, if you need to have multiple, accesses to the same data element, what happens in CUDA, sort of the implementations, is that they added this shared memory. Okay, so that you can actually just load the data into the shared memory once, and then multiple ALUs can access them from the shared memory. And this conserves the memory bandwidth. The bandwidth out of the DRAM is actually pins. Okay, we're talking about GPU pins. And those pins are expensive. A typical chip that goes out today, the high-end chips, have about 86.4 gigabytes per second. And the next generation will be right around 100 gigabytes per second going between the GPU and the DRAM. However, the bandwidth here is at least an order of magnitude higher because these things are run by wires on chip. They're much, much cheaper, and they're also running at higher clock frequency. So that's why CUDA actually exposes this shared memory to the programmers. It's a controversial, topic. Some people say you shouldn't expose a shared memory to the user. You should just cache it, okay, and let program just let it use a caching mechanism so that you can actually just the programmers don't know about the shared memory. They still think that they're doing DRAM access, but it was just somehow transparently taken care of by the cache. The programming model for the memory space, you have seen this slide. Okay, this should be the second time you have seen this slide. Okay, so it's fairly it's important enough that we're going to show you multiple times. So we have registers that are going to be per thread, and we have local memory that is going to be per thread. Be careful with local memory. In the current generations, local memory is actually in DRAM. Okay, it's called local memory, but it's not local at all. It's very far away. Okay, it's local in the sense that it only can be accessed by the thread. Okay, but it can be only accessed by the thread in a very, very slow way. Okay, don't be surprised. Okay, so avoid this at all costs. Okay, and shared memory is per block. Okay, this goes to all the threads in that block. They can read and write that shared memory and make the data visible to each other. And this is the collaboration mechanism for those 512 up to 512 threads in the block. Then there's a rewrite, to the global memory, and this is in DRAM. All these three are in DRAM. Global, constant, and texture are all in DRAM. So essentially, you can have rewrite for global, and read only for constants, and the read only for texture memory. Usually what happens is the CPU will initialize the constant and texture memory, and then the GPU will just use it on a read-only basis. Okay? And a very common programming pattern for writing a piece of code on this machine is that local and global memory reside in the DRAM, much slower access, so you avoid them as much as you can. So the way to do it is to perform computation on the device to block, or actually I would change that to tile data, because this word block is used too many times in this lecture. I would call it tile data to take advantage of the fast shared memory. So what happens is you take the enormous data structure, you divide them into tiles, okay, and you bring those tiles into shared memory. Hopefully, what happens, if we go back to the slide where we show the pins and so on, that we will bring a tile of data that encompasses data 0 to data 3 into the shared memory. And then all the ALUs will be accessing the whole entire tile. And then you move on to the next one. Okay? So whenever you can partition your data in this form, you can use this machine extremely efficiently. So that's why you need to partition into data subsets, and you handle each data subset with one thread block only. And you load the subset from the global memory to shared memory using multiple threads to exploit memory level parallelism. Let's say if you have 256 data elements in your tile, instead of using one thread to load it 256 times, you should generate 256 threads. And each one will be responsible for loading one of the elements so that you can take advantage of the parallelism when you load them all into the shared memory. And hopefully the 256 loaded into a shared memory will be used by thousands and thousands of times across these threads to take advantage of the locality, and then you will move on. Performing the computation on the subset from the shared memory, and each thread can efficiently multipass over the data element, and then you copy the result from the shared memory back to the global memory. So in terms of matrix multiplication, we're going to come back to this point and show you how you can dramatically reduce the memory access bandwidth, okay, by using shared memory on tiled data. Texture and constant memory also reside in the DRAM. It's much slower access than shared memory, but they're cached, okay? So a very common programming pattern for this is that if you have a kernel that needs to access a variable that has the same value across all the threads, right? So for example, you're solving some kind of fluid dynamic system, and you have some kind of constant across used across all these things. So what you would do is you would use the constant memory and initialize a variable with in the constant memory. As soon as you use it, it's going to be implicitly brought into a cache. Okay, and that cache actually has a very high fan out from each location to all the streaming processors in the same 8 processor unit. And that broadcast mechanism will allow all the threads to access that same value in one clock cycle. And that can give you very high efficiency in accessing these. So you carefully divide data according to access patterns, and essentially a summary of what what we talked about before. If it's read-only access and mostly constants, not big data structure, you put it into constant memory. And if it's read-only access, you put it into texture memory. And as a side effect, you could use some of what we call the filtering kind of computation in the texture memory, but we may or may not talk about it. Rewrite shared within the block. You have shared memory, and this is going to be, heavily used in pretty much all your assignments. And then the registers, you don't really explicitly use registers, but all the local variables, or all the local variables that you declare in these functions, in the device functions, gets pretty much automatically assigned to registers until they run out. Whenever they run out of registers, you get into serious trouble. Okay, so that's one of the performance cliffs. And I'm going to come back to this point. Whenever you can conserve the use of registers, it's a very good thing because it allows you to run a lot more threads on the hardware at the same time. You can declare lots and lots of threads, but if the hardware cannot run a lot of them at the same time, you're not going to get performance. Okay, so using fewer registers will allow more threads to run simultaneously on the hardware. And then rewrite the input results and so on. You go use global memory. Hardware implementation. Okay, so now we're cutting a little bit deeper into how the hardware actually works. So this is a simplified version of what we showed in that big picture. Every 8 of those streaming multiprocessors form a streaming multiprocessor, and so the device is really 16 of these multiprocessors, and each one will have 8 of those processors. So that gives you the 128. Each multiprocessor, contains, in this generation, 8 of those 32-bit processors, and it's a single instruction and multiple data execution. That is, the instruction unit, the instruction unit will fetch the instruction, and it will control all the processors to do the same thing in one clock cycle. Okay, they will all do the same things. So this goes back to the reason why he asked the question about, what if you have, if and else kind of thing, if you have, different decisions. So you can easily imagine that, for a piece of code that, you may have in the kernel an if and else, and let's say processor 1, processor 2 will take the if part, and then part, and processor 3 through 7 will take the else part. The instruction unit will actually do the following in the current generation. It will actually fetch the instructions from the then part. Okay? And each processor will also determine that only these 2 processors should take the then part. So you will only activate those 2 processors during this period of time. So you will execute all the instructions on the then part by activating these 2 processors. Okay? And then after you are done with the then part, you go back and execute the else part. Okay? And at this point, you will activate processors 3 through 7. That's why whenever you have what we call a divergent execution path, among these processors, you will end up executing longer because it takes multiple paths, and each one will contribute to execution time. They all add up. Okay? How does this correspond to the threads? What happens is that you will have up to 512 threads assigned into a multiprocessor. More specifically, 32 of those form a warp. Remember that warp thing? Now I'm getting back to this. 32 of them form the SIMD unit. Okay? So in particular, you will actually, in the implementation, whenever the execution of threads in a warp diverge, then you will have this behavior. So let's say I have 512 threads in a block. right? That gives me, what, 16 of those warps, right? I can actually diverge between a thread in warp 1 and a thread in warp 3. I'm not going to suffer in performance because only the threads within a warp will trigger this kind of behavior. And what that tells you is what the hardware really does is it breaks down the block into multiple warps, and each warp will actually independently use the instruction unit. Okay, that's really what's happening in the real hardware. So that only when the execution diverges within the 32 warp unit, 32 thread unit happens, then you suffer the performance penalty. Okay? At each clock cycle, a multiprocessor executes the same instruction on a group of threads called warp. That's pretty much what I said. And then the number of threads in a warp is the warp size. And the current generation uses 32. It may even go down to 1 in the future. When that happens, then you essentially will not have SIMD SIMD overhead when you have controlled flow. So we already covered this thing. Each block of a grid is split into warps, and each third block is executed by one multiprocessor so that the shared memory space resides in the on-chip shared memory. And let me see. Is there something I need to cover in addition to what I just said? A multiprocessor can execute multiple blocks concurrently. Okay. So this is something that I just want to add a little bit more. Remember, each block, all the threads in the block will be assigned to the same streaming multiprocessor. But you can only also have multiple blocks all assigned to the same simultaneous the streaming multiprocessor. All those blocks will end up sharing resources, in particular registers and shared memory. Okay, and this is a little bit different from the threads in the CPUs. Usually, a thread in the CPU is an abstraction of the processor. So, x86, each thread will have access to all the CPU registers and all the CPU memory space, and they will have separate, entire set of separate registers accessible by each. Here, there's really just one big register file that will be accessed or shared, dynamically partitioned across all the threads that are running on the streaming multiprocessor. The current generation is 8,192 registers. So if you run, let's say, if you want to run 512 threads, okay, on a streaming multiprocessor, I don't care how many blocks, how you organize it. Just let's say you want to end up with 512. If you use 10 registers per thread, which is not a huge number if you think about it, that's 5,120 registers right there. Okay? So if you use something like 13 registers, you start to run out of registers. And the hardware will adjust to it by reducing the number of blocks that you can admit. So let me give you one scenario. Write down the numbers, okay, just so that it's easier to follow. Let's say I have 256 blocks, 256 threads per block, okay? And I want to end up with 3 of those blocks in a streaming multiprocessor. That should give me, calculate real quick, 768, right? 768 total threads I want to run on that multiprocessor. Let's say if I use 11 registers per thread, what's going to happen? How many registers are we going to use? Someone give me a number. 8,448. Is that number bigger or smaller than 8,192? Bigger, right? I'm not going to insult you by waiting for you to answer that, right? It's bigger. So we have a problem, right? We don't have enough registers in that case. The hardware is going to reduce the number of threads running on the processor until it fits. But the granularity of reduction is going to be on a block basis. So rather than just reducing enough threads to fit into the registers, you will take out one of the blocks. So now you're going down from 3 to 2. Okay? And that means you're going to have 512 threads rather than 768 threads. You immediately take off hundreds of threads when this happens. And what really happens in reality is oftentimes you may be using 10 registers per thread, and you manage to get all the 768 threads running, right? And you made a little bit change to the code. And you didn't realize that the code ended up using one more register. And suddenly, what you very carefully crafted, the code that you're so proud of, that should run so much faster, ended up running slower. Because underneath you, because you just used one more register, the hardware took out 1/3 of the threads running. Okay? Suddenly you lost performance. Okay? And we're going to go back to this point. But this is the first taste of what we call the performance cliff on this piece of hardware. Sorry. So that cliff is something that you want to stay away from. Okay? A multiprocessor, okay, that's the shared memory. And the shared memory capacity is 16K bytes. If you exceed that number, same thing happens. The number of blocks that can run on a multiprocessor will be reduced. Okay? So, I don't think we need to have, this is just kind of a very quick summary of all these things that we said, and it's mostly for your benefit, for your quick reference in the future. Okay? It will take a little while for you to remember all these things, so we, prepared, some of these things, some of these things to remind you of, some quick numbers. 32 threads in a warp, up to 16 warps in a block, and each block executes on a single SN, and GAD has 16 single streaming multiprocessors, at least 16 blocks required to fill the device. So this is something that, rule of thumb. In the current generation, you need to have about, no less than 200 threads per streaming multiprocessor to get into the performance range that you want. Okay, anything less than about 200 threads per SM is not going to get you very good performance at all. So just to get into the club, you need to have about 200 of those. And because the blocks, remember, the blocks are assigned to the SMs, right? And you have how many SMs? 16. So you need to have at least 16 blocks just so that you will occupy all the SMs. And you want more than 16 to have multiple of those on the SM so that you can actually get utilization. But without 16 blocks, you're not even in the game. You're not even using all the SMs. You're going to be losing entire SMs from your execution. Okay, that's really what we're trying to say here. More is better. If resources, your register thread space, shared memory allow more than one block to occupy each SM, and that's where you really start to hum. Okay, so I'm going to really wrap up very, very soon. I promise essentially to end about 11 o'clock. We're running a little over time. So, there's a little bit terminology review, and I'm not going to go through this, but, do yourself a favor, go through this slide and make sure that everything makes sense to you. If it doesn't make sense, come back and ask. Okay? This is we're very first quick, test for yourself. Access times. Registers, pretty much one cycle. Okay? Shared memory, about one cycle. Local memory, no limit. A minimum of 200 cycles. Okay? Global memory, no limit. Pretty much more than 200 cycles. Constant memory, varies. You can, the first access will be long, but then once it's cached, it's pretty much